All right. Hello, everyone, and thank you for joining this, our latest in our global webinar series. And the topic of record today is dispelling common inductor myths. So over the last couple of weeks, we've been going over some basics on inductors, and we will finish that series today with dispelling some of the common inductor myths as seen by some of the FAEs in the field. So with us today are two of our FAEs, one from the Americas and one from Europe. And we have Peter Blais, our Senior Director of FAEs in the Americas. Peter, if you'll please say hello.
Good morning, afternoon, and evening to everybody.
Okay. And we also have Alexander Nabel from the Europe region. And Alex, would you please say hello?
Yes, hello to everybody, also from my side.
Okay. And then there's myself. I'll be your host today. My name is Wilmer Companioni, and I lead our technical marketing team. And as you can tell, I'll be your host for this webinar. So let's just get right to it, gentlemen, shall we?
Absolutely.
So I'm sure you guys have seen many interesting questions and many interesting use cases of inductors in your experience in the field. And the myths and the misconceptions that we've identified today are some of the more common ones that you guys have seen. So let's get to it. These are the four that we'll be talking about. Some of the top inductor misconceptions, if you will. This idea, first off, is this idea that you can always make inductors smaller by continuing to increase that switching frequency. Then there's the notion that reducing that core loss is most important when accounting for magnetic losses or inductor losses, really. Then the idea that rated current, saturation current are kind of the same thing when comparing across inductor manufacturers. And finally, the last myth will be dispelling or clearing up is the idea that for equal inductance and current needs, you can sort of choose either ferrite or metal composite inductors with no real issues. So let's take it from the top, the first one. I can always make my inductor smaller by increasing my switching frequency. I think, Peter, you're going to take this one. What is your take on that, and what happens, and why is that not necessarily true?
Well, Wilmer, this is a great question, and if you just look at it from a theoretical perspective, the statement's correct. If you go up in frequency, everything's going to get smaller. That's what the electronics industry has been doing over the years. However, we don't live in an ideal world, and there are losses associated with materials as you go up in frequency. And if we take a look at magnetics, one of the big issues is core loss. And as you go up in frequency, the materials that are used to basically increase the magnetic field going through them, which increases the permeability of the component, as those tend to get higher in terms of increasing permeability, they also tend to get lossier as you go up in frequency. So if we take a look at this graph here, you can notice that for ferrite material, they are very, very efficient as long as you stay typically below 1 megahertz. And as you go above 1 megahertz, you start to induce losses. So what happens is you can go up in frequency, but if you are dealing with a high power system, such as large servers or cloud infrastructure equipment that's very high power, you end up having increasing losses as you go up in frequency, and you may be able to make the components smaller, but your whole power scheme to compensate for the increased losses and heat generation actually make everything bigger. So that is the, I guess the challenge going smaller is tied to the material losses, particularly in ferrite, which is has a lower loss core material than metal composite.
Okay. Yeah, and so it appears that you kind of get into this area of diminishing returns, if you will, as you attempt to go smaller by increasing frequency.
Right.
Alex, do you have
particularly with the higher power systems? Particularly with the higher power systems, if it's a very low power system like a cell phone, you can go smaller because the power starting out is so low, then your increase in losses is frankly negligible.
Okay. Alex, do you have anything to add to that, to some of Peter's comments?
Yeah, it's the same experience I have made like Peter. We always need to be careful by downsizing, also considering the frequency range of different materials. Like we can here see now on the screen that metal composite and manganese zinc ferrite are acting differently. And this needs to be considered when you choose the right inductor for your application. This is something, and we will also talk about this in one of the later questions. Okay,
thank you, Alex. Okay, so next up is, when speaking about losses and magnetic losses, next up is this notion that core loss is most important, right? So we've talked about core loss and your choice of what magnetic material and the composition is the idea that, yeah, choosing that right material, that's most important to take into account when accounting for magnetic losses or losses in magnetic components like inductors or even chokes. So is that true, that all you just worry about reducing core loss and everything is fine?
So when we take a look at losses, you've got core loss and then you've also got conductive loss. And if we take a look at, let's take a look at two circuits. One of them, let's say it's a resonating circuit where you're switching between positive to negative in a sinusoidal fashion. Well, in that case, there's no DC, and all of your losses, or the majority of your losses, will be core losses. And so the core loss and also the geometry of the component becomes critical. But that is not the typical application that we see for inductors. Most of the inductors that are designed into power distribution systems today are used in a predominantly DC function with the AC ripple superimposed. So when we take a look at that, the power going through the inductor is predominantly DC, it's not AC. At which point your losses are going to be skewed away from core loss and directed towards conductive loss, which would be copper loss here in this graph. So as you go up in amperage, your losses for DC applications are going to become very, very dominated by the copper loss or conductive loss of the material. And that's where the configuration of the winding, the geometry of the conductor, in terms of the cross-sectional area of the conductor, the number of turns, so on and so forth, that becomes very, very important. And of course, for efficiency, we want to go and minimize that core loss or DC resistance associated with the magnetic.
Okay. So yeah, you get to this point where you can, this certain operating point where it becomes reasonable to reduce your core loss. That's fine. You got to worry about that. But then there's a point at which, I guess, Peter, you cross over, and then those copper losses, those conductor losses, they become more important than even the core loss.
Absolutely correct.
Alex, do you have anything to add to that?
Yes, I can add also one aspect to Peter's explanation, and also the inductor itself acts as cooling item. So when you reduce also here the size, you have less cooling capability. And the same is also finally, which makes it more complicated, the PCB and the wires on the PCB, which cannot be actually calculated or simulated because it depends on the final application of the developer. But here we also see the link to the first question. Reducing the size of the inductor means also higher copper loss because you have a smaller, or let's say a thinner wire, and you have a smaller item which has less or worse cooling capabilities.
Yeah, that's a good point, Alex. So then it sounds like you can almost compound these two things together. You go smaller and smaller and smaller in an attempt, or higher in frequency in an attempt to make the inductor smaller, but you start to experience more loss in the core material itself. And on top of that, what you're saying, Alex, is you also start to experience more copper loss as well, because I guess your wires are getting thinner, right?
Right, yes.
Yeah. Okay, next up, rated current and saturation current. This idea that we're comparing across two different inductor manufacturers, and they state rated current and saturation current, and even if they're the same, you can feel like they're equivalent to each other. Is that true, Alex? That when comparing across manufacturers, you can just compare the saturation current and rated current?
Well, it would be so easy, but unfortunately it isn't. So there's no standard in the world of manufacturers which says that the saturation current or the rated current has to be exactly the same. So there's no rule, no standard, and this means every manufacturer can do it in their own way. And finally, when you look into the data sheet, and here you can see a screenshot of our data sheet, we describe the rated current and the saturation current is just 1 point on a curve. So it's actually describing only one certain point. And sometimes you can see that the inductance drop is described at 20% drop, and sometimes it's 30% drop. And it could even be anything else. And I've seen in many different manufacturers that they are using different values. Also for the temperature rise, this could be 40K like we see here. Also, it could be 30K. And why is there no standard? I don't know why nobody decided to do a standard and everybody does what he thinks is the best. Actually, we are giving in our data sheets 2 different saturation currents to make it a little bit easier to compare to competitors. Because here now you can compare the 20% rated current point or the 30% to any competitor. Because sometimes it could be that the same item with the same size and value has a saturation current given of 30%. But if you compare them now and say, oh, well, I found a coil which has 10 amps and the KEMET coil has only 9 amps, then maybe you need to read twice and need to read what is written below the graph. And here we exactly describe the difference of the IRMS or rated current and the saturation current. And unfortunately also, one supplier can have different saturation currents in different series. And this might be much more complicated. So don't think that it's always the same. Please read what is written below this table.
Yeah, so it seems like you have to be very careful looking at when manufacturers define their points of rated current and saturation current. You have to say, well, as you're designing that in, you have to say, well, under what conditions is that number defined to be?
Right.
Peter, have you come across any instances in the field where maybe some people get these mixed up, or they think that, oh, going from one manufacturer to the other is fine, and then they have this uh-oh moment that they didn't read the fine print and they kind of got in trouble there?
It actually happens very frequently, and what the customer, the designer needs to do is look at the use conditions of the component and then evaluate the performance of the inductor under the use condition. And I remember one actually it happens a lot of times, but you may have two inductors, same inductor value, same equivalent dimensions, and construction or similar construction, and vendor A will have actually a lower DC resistance than vendor B, and however vendor B would have a higher current rating for the component. And going off of the data sheet, you think vendor B is a better component. But if you dig into the data sheet, factoring in temperature rise, allowable temperature rise, vendor B may have a much higher allowable temperature rise than vendor A, but vendor B also has a lower operating temperature than vendor A. So what you end up doing is, under the use condition, you actually find out that you can put actually a much lower current through vendor B than you can through vendor A, even though on paper vendor B looks like a better component. So it is a bit, the devil's in the detail. You have to go and look at the specific use condition of the component and compare the two vendors.
Yeah, the conditions under which these rated or spec'd out numbers have been determined.
Correct.
Okay. So then, again, with this, this idea of comparing across different vendors or even different technologies, there's this possible idea out there in the industry that when you're comparing across different inductor technologies, yeah, for equal inductance and current needs, right? I have my, let's say 1 microhenry of inductance and one amp of current, and I find those two things being equal, I can go either ferrite or metal composite, and I'll be all right. There's not going to be any issues to that. Alex, is that sound thinking? Is that an okay way to think about it? That if everything is the same, then it's a toss-up whether ferrite or metal composite?
In an ideal world, maybe, but we are not living in an ideal world. So actually, this is like if you want to change from electrolytic capacitor to film or MLCC without thinking about their different behavior. And it's unfortunately much more complicated because you have to consider much more than just the inductance and the current of the used inductor. There's much more, like the RDC or the impedance. And when it comes to also to the structure, like we can see here on the picture, if you take a molded inductor or an assembled inductor, there's also a different behavior in EMC, because this assembled inductor we can see at the bottom has, let's say, an air gap, which is also at the outside of the component. And this means we can have magnetic field at the top of the assembled inductor. This creates, let's say, a worse EMC, which is not with the molded inductors. So it's not that you just change from from product A to product B and just say, okay, this is a 33 microhenry coil, let's take it. You have to consider the different material. And also, what we have seen before, the frequency range might be different. So each material has its own perfect frequency range and cannot be used at higher frequency range, because then the inductor starts to create more and more losses. And this is something we don't want to have with our inductor. So, and what I didn't mention before, but I can also already see one question. There's also one difference when it comes to round wire or flat wire technology. So also this has an impact on the different behavior of an inductor. So it's not only the inductance and the current of the inductor, but much more than this. And let's say it's the material and the structure.
Okay, thanks, Alex. And Peter, I think you've seen a case out in the field where somebody chose one of these assembled type inductors and without necessarily considering the flux leakage here, and that kind of got them in trouble with some induced eddy currents, right?
Absolutely, and we see this happen periodically. So a lot of your ferrite inductors are inherently unshielded. There's an exposed air gap in them, and magnetic flux can leak out of that air gap. We've got in the picture here, it sort of illustrates that. And I can remember we had a customer, and there was a piece of metal, part of the housing, that was a ferrite-based metal that was in very close proximity to an inductor. And when they used a ferrite inductor, it created some extremely high eddy currents in the cover, causing actually some significant heating and also corresponding power loss in the system. So by switching over to a metal composite, which is inherently shielded, that eliminated that design problem. But in general, most people start with choosing either a ferrite system or a metal composite system based on the intended application of the system. Of course, metal composites, the reason why you choose them is because of the soft saturation. So if you need a system where you've got a very predictable inductance over a broad temperature range, especially as you go to the higher temperatures and as you go to the maximum currents versus low currents, then you want to obviously use metal composite. If you get a system where you, even at elevated temperatures, you're staying below that range where the inductance drops off drastically, then your ferrite tends to be a good choice because it does have lower losses, particularly at lower frequencies, than the metal composite. So again, what you need to do is you need to evaluate all of the pros and cons based on the way you're using your system, and also the mechanical configuration of the system, because again, if you've got, say, a ferrite material in close proximity to the air gap, you're going to be inducing eddy currents in that material that are close to the unshielded ferrite inductor.
Yeah. As you said, Peter, the devil's in the details, right, for some of these things. At first glance, it might look like you can do an easy switch here between ferrite or metal composite, but if you don't take into account that flux leakage, you might find yourself in an unfavorable situation. Okay.
Absolutely.
So let's recap here a little bit. Let's go over these four myths that we just talked about. First off is this concept that I can always make my inductor smaller by increasing the switching frequency. And we've learned that there is a point of diminishing returns where that core loss can actually start to increase and make the solution less efficient overall. And continuing along the theme of losses, the notion that reducing core loss or going for an inductor with lower core loss is most important when accounting for losses in inductors. And again, that's also false, because depending on your operating circumstance, there is a point at which the copper loss dominates over that core loss. And we learned that rated current and saturation current are not necessarily the same when comparing across manufacturers. There can be variations in the definitions of those very terms across different vendors. And finally, even though your inductance and current needs may be in a range that is acceptable or suitable for ferrite or metal composite structures, that doesn't necessarily mean you can choose either one. The choice in capacitor determines how much loss, EMI, and even saturation you'll experience. So now we'll take some questions, and I'm sure I can already see that we've had a few come in. Please submit them. If you have any questions, submit them through the Zoom window, and I'll be sending those to our speakers, and we'll be discussing those here in the next minute or so. And if we go over time or some questions come up after the fact, you can always submit it on the link that's on the screen. So let's go through some of these questions now. I guess the first one is, do KEMET magnetic cores get manufactured by KEMET, or are they purchased from somewhere else? So basically, do we own that core material? Do we make it? Peter, I think this is right up your alley.
So the answer is we manufacture our own core material, but we go beyond that. The actual formulation of that material, the technology behind that material, we develop in-house ourselves. So that's done by our team in Japan in terms of the development of the materials. That's whether it's ferrite or metal composite or more advanced materials that are in the pipeline. And then the actual ferrite manufacturing, where we've got the large ovens that center that ferrite, that's actually done in our Xiamen factory in China. So yes, the answer is not only materials development, but the manufacturing of those materials all done in-house.
Okay, and Alex, I think this one might be good for you. Do you have any suggestion about the distribution of core and copper loss? I guess this question in particular refers to the fact that a while back, some time ago, there was this sense that the total loss was pretty evenly split between core and copper. But now I think we've discussed a little bit that it all kind of depends at this point. So do you have anything to add, any guidance, where is the better spot to be, core or copper loss?
Well, that's correct. I know this rough estimation. As we have seen today, it's not so easy to make a clear 50-50 or 60-40 distinguish, because it depends on so many things, like we have seen before: material or building structure and frequency range, current. So what I can say is it's finally up to the designer to find the right component. If I go bigger and bigger and take a component which might be too big for my application, so take more than I finally use, then for sure the copper loss decreases. But at the same time, we want to save cost and we want to save space, which means I get smaller and smaller, and this means my copper loss increases more than the core loss. So it depends on how perfect my choice finally is. And I cannot make a rule of, let's say, 50-50 or 60-40.
Okay. So I think this leads pretty well into this next question is, when considering things like skin effect and these things at high frequency operation, which tends to be higher, core loss or copper loss?
This is interesting. Unfortunately, we did not go too deep into the proximity or skin effects, but I mentioned, for example, the flat wire construction, which is ideal for higher frequency because the skin effect is usually happening when you have higher frequency and the full, let's say, the size of the copper wire cannot be used, as at higher frequency the current is only at the surface of the wire. By using a flat wire, I have more, let's say, surface, because a rectangle has always more space than a circle, or let's say more surrounding than a circle by using the same amount of material. And this is important to reduce the copper losses at higher frequency. And this is the main difference when you use, let's say, also the GPI series we have seen before, which has only one turn and has a very thick flat wire.
Okay.
Wilmer, if I could add to that a little bit, given a real life example, and it's a little deviation from a surface mount inductor, whether metal composite or TPI ferrite. But we had a customer that we were doing a custom choke for, and we actually did some evaluation, and this was a higher frequency system, a high power, high frequency system. And we evaluated round wire, and then we took it a step further, taking a look at Litz wire, where, of course, Litz wire is a very fine braid of lots of individual copper wires. So you've got a much broader or much larger surface area or skin versus inside the copper wire. So it drastically reduces skin effect. And what we found is by switching over from solid copper to Litz wire, we were actually able to reduce the heating of the system by more than 50%. So that just illustrates that your skin effect actually plays a significant role as you get up into the higher frequencies, especially with high power systems. So if you're looking at, in this case, I think it was a high power solar conversion system. So there's no simple answer. You need to take a look at everything, but skin effect can have a significant contribution, especially high power or higher frequencies.
Okay. So actually, this leads pretty well into this next question here, which is, where does high frequency start? What's considered high versus low?
This is a good question. There's no rule, I guess, where we can speak about high or low frequency.
I think it deals with the power level of the system. If you look at, say, cell phones, high frequency is getting above several megahertz, like 5 to 7 megahertz for your switching power circuits. If you look at servers, the boundary today for your power distribution, because it's, you're dealing with, in some cases, hundreds of amps of current for your processor cores, that tends to be in the megahertz range. If you look at big systems like big inverters, like whether it's for an electric vehicle or solar inverter, you're in the range of 30 kilohertz to a little over 100 kilohertz. There's some exotic systems that push it into the very low hundreds of kilohertz. And really the limitation is for these big power systems are the losses associated with the magnetics. That's really the limiting factor for the switching frequencies of these big power systems.
Okay. So we'll take one more and then we'll have to move on. I think we're just a little bit over time now, but good discussion. I'll try to summarize this last question here pretty briefly. But the spirit of the question is, what are some of the factors that affect the life of an inductor? Is it temperature, the amount of current you're putting through it? What are some of those key things to look at, or when trying to take into account inductor life?
Well, this is maybe a little bit easier to answer, because the good thing is the only thing what we are using by manufacturing an inductor is a piece of copper and a material around that. So by looking in the world of capacitors, it's much more complicated, and we always have the situation with lifetime. Actually, with an inductor, you don't have that much limiting situations. There might be a situation with humidity, temperature, but in the normal lifetime of any PCB, the good thing is lifetime of the inductor is not that bad issue. Maybe only if you have some special, some glue or some resin, which is not the standard item, because our metal composite inductors, for example, they are only having their copper wire, their connection, and the metal composite material, which makes it very easy, and it's a long life component.
Okay. Thank you, Alex. All right, that was all the questions we had come through. If you have any others, submit them there on go.kemet.com/contact us, and we'll get to those at that time. So before we close up today, and thank you, Alex, thank you, Peter. I'd like to promote some of our upcoming webinars. Actually, this day is wrong. We're moving on to a webinars on every Monday. So starting on July 6th, we'll be discussing solutions for uninterruptible power supplies. And then the day is wrong there. It's not Wednesday, July 13th. It's Monday, July 13th, where we'll be discussing solutions, EMC solutions for conducted and radiated emissions. And then be sure to follow us, register for some of those webinars, and follow us on those social media channels if you haven't already. And you can get more information and more things about our upcoming content and webinars. And with that, Alex, Peter, gentlemen, thank you very much. Very informative, very educational, and thank you everybody for attending this webinar, and we'll see you on Wednesday. Wednesday, we have an important one, a big one. Our Chief Technology Officer, Phil Lesner, he'll be taking us through a look across the frequency spectrum and a look into the future of our passive components. So that'll be an exciting one with a great presenter, Phil Lesner. So everybody, thank you for joining, and we'll see you on our next webinar.
Thank you, Wilmer. Our pleasure.
Thank you and goodbye.